Okay. So I repeat what I was saying before. Can you hear me now?
Yes, good morning.
Yes, okay. So thanks to the chairman, I wish a good day to everybody, and thanks to the Xiamen University staff for the organization of this conference. This is my first conference on the cold diffusion field. In the past, I worked with ENFN in high energy and particle accelerator physics and in cosmic ray physics. Perhaps now it's time for me to move to a lower energy sector. I shall report in this talk on a preliminary test which was performed in November 2019 at the Helmholtz-Zentrum Dresden-Rosendorf in Germany, just before the start of the pandemic. I will start with spending some words on the theoretical background, which is mainly due to the multi-years work of Professor Vysotskii, who will follow me in this conference. This is the sake, the reason for this is clearness, completeness of information, but also because I was particularly attracted by this model because it shows a predictive capability and is based on universally accepted physics, unlike most LENR models, which have sometimes an heuristic character and often invoke new principles that have no evidence anywhere else. So let me move now to next slide. From the genial intuition of Heisenberg, we should specify that this question of correlated state is strictly connected to the history of the progression of the uncertainty relation. From the Heisenberg genial intuition, then was Kennard, a young American postdoc, which gave the final formulation, which we found nowadays in all textbooks on quantum mechanics. Then Robertson extended the relation, the uncertainty relation, to the case of a couple of Hermitian operators, AB. And eventually Schrödinger observed that the further term should be included on the right hand side of this uncertainty relation. That's the case when the two observables as being statistical variables should be correlated. So there's a covariance term here. And then in the same paper, Schrödinger was wondering which aspect should have this CCS, I will call in the following correlated coherent state CCS, just CCS. And the first reply came 30 years later from Glauber. He recognized the coherent state of quantum optics as minimum uncertainty states. Then the existence of squeeze states which have the same total uncertainty but unequally distributed between the two quadrature variables was proposed and then also experimentally verified. And then finally, Dodonov, Kurmishev, and Manko gave a final formulation extending the coherence, the concept of CCS also to mixed states. And then in the same paper, they observed that a wave packet in CCS may experience a transmissivity through the Coulomb barrier much higher than in an uncorrelated state. So, but what this CCS would look like in phase space? You see here this shaded area. Sorry. The shaded area here is the uncertainty area. This is clearly the coherent state a la Glauber. The vacuum or 0 point state is a circle centered on the origin. Then if we introduce a squeezing factor K here, it assumes the shape of an ellipse. Then we can introduce a further degree of freedom by tilting the ellipse, and we have a vacuum state correlated state here. So the generic minimum uncertainty state will be represented by a graph like that. Of course, a non-minimum uncertainty state will be characterized by the fifth real parameters. So what is now, let me just do a simple summary. So we have now Heisenberg uncertainty relation. Then we have the Schrödinger-Robertson inequality. Then we can introduce a correlation factor R. So we can transform this uncertainty into introducing the concept of effective Planck constant here, where the on the denominator you find the term 1 minus r squared that may go. So this right hand term may go to the infinity when r goes to 1. So the transmissivity through the Coulomb barrier may increase enormously according to this law. And the CCS analytical expression can be obtained by proper canonical transform or from the solution of the time-dependent Schrödinger equation. Yeah? They have this form as found by the three Russian physicists. But how can we practically produce? We can think that the CCS may be produced by parametric process, in which you have here parabolic potential, just similar to harmonic oscillators, in which the frequency is time dependent with the periodical law. So we can show that the Schrödinger equation for non-stationary classical harmonic oscillator has a solution which are formally identical to CCS and depending on the solution epsilon t on this equation. By the way, this equation is very well known to accelerator people because it describes the Betatron motion. It's the Hills equation. Correlation squeezing factor can be expressed as a function of epsilon. But now, how can we realize this in practice? We can think of a particle crossing a potential well, as given by two atoms in a lattice structure. And the potential can be described by a parabolic function like shown before. And this, this is correct from channeling physics because this approximation has been done and works perfectly, although this phenomenon is completely different from channeling, which is a high energy phenomenon. So just a pictorial view, you see here, we can imagine of a particle crossing the crystal lattice. Then it experiences a transverse harmonic potential, and then a longitudinal modulation as soon as the particle goes through the crystal lattice. But the same situation occurs also in case of a diatomic molecule, because in the comoving frame of the particle, there will be some sort of Gaussian profile for the Fourier spectrum I've seen. And we can imagine, we can adjust the speed of the particles in order to meet resonant conditions as a parametric process. So in both cases, you see here that the correlation factor very close to 1 can be reached very rapidly. Now, in summary, in uncorrelated state, you can assume that the various Fourier components are completely, they have of course a delta p, but they do not add coherently, they just add quadratically, so the transmissivity will not grow in a significant way. While in the correlated state, they add linearly, so the interference term will have a strong importance. In practice, some calculation shows that for two important fusion process like a proton over lithium and the deuterium, the cross section may be enhanced up to values you see that are of the order of millibarn or maybe 100 of millibarn, so they are quite well measurable in a laboratory experiment. You may say this is just nice but pure speculation. Well, there are some experimental indications from the past there is an American independent group who did a lot of work spanning several years and doing experiments and tests on different accelerator facilities in the US. They irradiated both lithium vapor and lithium solid target using ion source. And in both cases, they observed at the energy in which we expect alpha particles from lithium-7 proton reactions, yet at the order of 8 MeV, a strong signal. In case of solid target, they measured a counting rate of the order of 100 particles per second, while in case of gas target or vapor target, this rate was of the order of 10,000 particles per second. So what we did, essentially, we had this reaction understood. We had a solid target made of polycrystalline lithium foil, and with the given thickness here. Then we had the ion source, Tetra plasma source, which irradiates this lithium crystalline target. We have an ultra vacuum chamber equipped with a silicon pips detector located very near to the target. We use a sample manipulator to position and rotate the sample holder to respect to the ion source. The current flow is measured by Faraday cap. So the peak energy is dictated by intrinsic plasma energy. This is a bit the critical point because we cannot have a precise measurement of the energy. There's this uncertainty. And the voltage can be adjusted using the inner grid, which is inside the plasma source, and can be adjusted. But of course, a precise measurement of the energy is not possible with this system. A word about background. The background here is mainly due to backscattering from target sample order. The detector is quite well shielded from cosmic ray, from gamma ray, because there's a gold foil around at the entrance of the detector, but also the entire detector is very well shielded. So we know from the information and the experience of German colleagues that the background is really minimum, perhaps from cosmic ray, 1 event per day or something like that. Unfortunately, since we are using very low energy, there is no possibility to calibrate the system because there is no resonance. In general, in all the experiments with the nuclear astrophysics, we have impurities in the target that may give rise to resonances that are useful in a sense that permits the calibration of the system. But in that case, it was not possible. But as an advantage, we have no gamma-like reaction.
Sorry, Professor Bartalucci, I have to remind you that you have 5 minutes more. 5 minutes,
okay. So this is an example of what we measured, no proton source. This is the spectrum you see here. And then this is just a single event we observed during one of the many runs we had on this point. So this is a picture of the apparatus and a picture view from the other side. This is the sample and holder without beam. This is the sample holder and the target irradiated by the beam. Now the experimental procedure, as I said, we had to look for this resonance. The energy of the protons, according to the recipe that I shown before, is of the order of 450 MeV. We expect for the parametric resonance. So we made a systematic scanning in the range from 300 up to 400 keV. Then we made also further scanning to look for the much weaker main resonance, because in the parametric oscillators we have also a weaker resonance at the same value of the unperturbed resonance. Then we use a bipolar supply also to apply negative voltage to the sample and order. In some cases, we tried to move the target to observe there was an angle dependence. So the instability also was a problem, but I mean, this is something intrinsic to the ion source. So finally, this is what we observed in just one run. You see an extra counting at the energy of around 8 MeV. And unfortunately, we was able to reproduce this result. And the reason maybe can be understood from the following consideration. So we have a pure monocrystalline, we should have for this experiment a pure monocrystalline target, but this is very expensive, it's difficult to handle because lithium is highly reactant. We should have also the enterprise that does not give the crystal orientation, so we need X-ray goniometry probably, and this is polycrystalline, cheaply foil is currently used. And maybe there are techniques also to, like electron baskettering method to make a characterization of the single grain, but this is also a step that should be done, complicated. Cleaning by ego spattering is not sufficient. So a future study of CCS should be made also in gasless targets, as theoretically described in your previous work, and observed in cited literature. And we think that the next step is just to equip, to make an equipment with the possibility to use this vapor tag. So finally, clear alpha signal was observed above the background at 8 MeV. Proton beam quality has to improve substantially. Accurate energy calibration and definition is required. High current, beam spot size control, this is very important. Ion source stability has to put in place. We need probably an electrostatic decelerators because to have a magnetic analyzer to define well the energy, then we should say decelerate the beam while preserving the quality of the beam. The target is the crucial issue in the search for CCS. Future experiments must host both solid and gas targets. This is a search for a rare event, as in all LENR-related activity. Much time has to be allowed for test preparation and running, especially with compared to previous work. You should understand that I had only 2.5 weeks to make such measurement, that I found all the materials and all the equipment already in place without much possibility to control and to overview the preparation of the test. This is not the usual practice in physics. Hopefully, a best suited facility will soon be available and for more accurate experiment according to above prescription. And then I know I'm also participating in this Klein HME collaboration, which was presented by Professor Czerski, I think the first day. So I hope that they have a good facility, and I hope that with the requirements that I stated above, it will be possible to make accurate measurement and to confirm definitely this very important result. Thank you very much for the attention.
Thank you, Professor Bartalucci. We have 1 minute for questions. If someone in the audience likes to ask Professor Bartalucci, please, this is the right time. Professor Bartalucci, if I can, how you may extend these interesting results to the deuterium behavior in condensed matter?
That's, I thank you for this question, because it's a thing that I wanted to investigate. In principle, I mean, to find the deuterium crystal lattice, I think does not exist something. We should consider the possibility to use a deuterium vapor and to irradiate a deuterium vapor with the deuterium beam. That's a possibility that, according to this model, to my opinion, is possible.
Okay. Thank you, Professor Bartalucci. So if we don't have any additional question, I think we have to move to the next